Let's look at this chapter 16 and 17. 8 questions for reviewing for our test. And it wants to know how many grams of solid potassium fluoride should be added to 1 liter of a 0.25 molar hydrofluoric acid solution to prepare a buffer with a pH of 3.816. So I see the word buffer. Buffer means we're using our Henderson-Hasselbalch equation. Now we are given the pKa of HF is 3.14. That's because we know the Ka for HF given to us in our appendix, but this just made it a little bit easier. So we look at our Henderson-Hasselbalch, we know our pKa, and we're told the pH we want it to be is 3.816. So I'm just going to plug in that 3.14 pKa and 3.816 and leave this be for a minute. Yes, we are given HA concentration, but let's just solve for this piece here and then work. So I'm going to subtract the 3.14 from both sides, and I get 0.676 is equal to the log of the concentration of our salt over the concentration of our acid. Now, to get rid of the log, we need to take both sides, and we know log is base 10, so 10 raised to the 0.676 will just give me concentration of salt over concentration of acid. So 10 raised to the 0.676 is 4.74, and that's equal to the concentration of the salt over the concentration of the acid. Now we were told that we had 0.205 molar of hydrofluoric acid, so now I'm going to plug that in there, 0.205 molar, and I'm going to solve for the concentration of the salt, the potassium fluoride. So I'm going to multiply, here we go, concentration of A minus, which is the salt, the potassium fluoride, Kf, is 4.74 times 0.205. So that is 0.972 m. That means moles per liter. It wants grams. How many grams of potassium fluoride should be added? Now, if I know moles, I know moles to grams is just one more little step. So I found the molar mass of Kf is 58.1. That would give me 56.5 grams of potassium fluoride would needed to be added to 1 liter of the hydrofluoric acid to make a buffer with a pH of 3.816. Let's look at number 2. A buffer solution, again, that's going to tell me Henderson-Hasselbalch, contains 0.464 molar ammonium bromide and 0.309 molar ammonia. So we're told that we have this many moles of potassium hydroxide added to 225 milliliters of this buffer. What's the pH of the resulting solution? All right, let's write down what we know. We're given a concentration of ammonium bromide, and ammonium bromide is a salt. We know that. Bromide is a halide and is a salt solution. We know ammonia is a weak base. So we want to know how many moles of each do we have, because we're told moles of potassium hydroxide, which is a base, is added to it. So because we have moles of that, let's get moles of both of these concentrations. Again, to find moles, we take concentration times volume. So I'm going to take my 464 molar times 0.225 liters to get 0.1044 moles of our salt. I'm going to find moles of my base by taking 0.309 molar times 0.225 liters. I get 0.0695 moles of my base. And of course I'm given more base, more potassium hydroxide, 0.0340 moles added. So let's do an ice table here. When I have my salt solution, and I'm going to add more hydroxide, that potassium hydroxide. And so we know that this salt solution is going to donate a proton, so create water, and then leave me with NH3, the ammonia. Now initially I have my salt solution, 0.1044. This is the hydroxide I added more of. And remember, initially I do have some product. This is the ammonia. I'm also forming more product, but I initially have 0.0695 moles of that. So we can see here the smaller of the two reactants is 0.03, so we're going to completely use up that hydroxide. So subtract reactant, add to product, giving me total number of moles of ammonia, which is my base, and total number of moles of my salt. Now, because I am starting off with my weak base ammonia, and because I'm adding strong base, I'm going to look at my Pkb value for ammonia, and that's 4.74. That also means, since I'm given all those base numbers and I'm adding base, I'm going to use my Henderson-Hasselbalch equation, but I'm going to do it slightly different. And instead of finding pH, I'm going to find my pOH. So I'm going to put in my Pkb and plus the log of my salt over my base. Looks very similar to pH is equal to the pKa plus the log of salt over acid. We're just making it basic. And basic means pOH, Pkb, salt over base. All right, so when I plug this into my calculator, I would get 4.74 plus a negative 0.167. So that would give me a pOH of 4.57. And how do we find the pH from here? Well, all we have to do is 14 minus the pOH to get the pH. We should get 9.43 for my pH. Let's look at number 3. We have a buffer solution containing 0.4 molar of NaH2PO4 and 0.320 molar of Na2HPO4. How do we know which one's which? Well, the one that has more hydrogens, this guy, is much more acidic. So this acts as our acid, while this guy acts as our salt. All right, so we're given concentrations of both, and we're adding perchloric acid to this buffer. So let's look and see what we've got. We've got the NaH2PO4, that's acting as our acid. Again, more hydrogens. There's 2 hydrogens in this guy versus 1 hydrogen here, so this acts as our salt. And then we're adding in perchloric acid. So again, I took our concentration times volume to get moles of our acid, concentration times volume to get moles of our salt, and we know moles of our acid that is added in. So I'm going to make my ice table here. I have my HPO4, I just took off the sodium because that's a spectator ion. So we have our HPO4 added to our acid that's added, the perchloric acid, I just wrote H+, and that is going to create our H2PO4, the acid over here. So initially, again, I started with 0.04 moles of our salt. I added in that acid, 0.0153 moles, and initially I started with a certain concentration of acid. Change. Again, this is my smaller number of moles, so we're going to completely use up the perchloric acid added in. So I'm going to subtract from my reactants, add to my product, giving me equilibrium values of 0.0247 for my salt concentration, 0.0653 for my acid concentration. Now I'm going to plug it into my Henderson-Hasselbalch, and I know my pKa value should be found in our appendix as 7.21. And then I'm going to plug my salt over my acid, and that would give me negative 0.422, and that should add those together to give me a pH of 6.79. Let's look at number 4. In the lab, a general chemistry student measures the pH of 0.520 molar of aqueous solution of phenol, which is a weak acid, with C6H5OH to be 5.127. use this information to determine the Ka of the acid. All right, let's look at what we got. We're given the pH of the acid. So from that, we can find the H plus concentration, or the hydronium ion concentration, right? By just doing 10 raised to the negative 5.127. So we get the H plus concentration of 7.464 times 10 to the negative 6 molar. Now we're going to look at this phenol, the weak acid, in its dissociation. All right, so we have C6H5OH added into water is going to, remember this is our acid, so it's proton donator, give us H3O plus, which is our H plus concentration, and C6H5O minus. Initially, we're told we have 0.520 molar, right? That's how much phenol we have, our weak acid. And we have no products yet. And we know we're going to lose reactant, gained product. So our Ka expression at equilibrium, we would say, is x times x, or x squared, over 0.520 minus x. Well, we just found that H3O plus, or the H plus ion concentration, x, is 7.464 times 10 to the negative 6. So we know x because of the pH that we were given up here. So we can now plug in that x into our Ka expression. So we can square our x and then do 0.520 minus x, and we get a Ka value of 1.07 times 10 to the negative 10th. Looking at number 5, we are looking at different species, and we're going to classify each of the following as a Lewis acid, Lewis base, neither, or both. So our first two, BF3 boron trifluoride, I just drew it out, and Fe3 plus. Now both of these are Lewis acids. Why? Well, a Lewis acid contains an empty orbital which is capable of accepting an electron pair from a Lewis base. So if we look at BF3, there's only 6 electrons in this central atom. So it's electron deficient. It would love to accept more. Same with this Fe plus 3. It gave away 3 electrons, so it has that empty orbital which is capable of accepting an electron pair from a Lewis base. Now let's look at the next two, O2 and pH3. So I just drew oxygen and pH3, and we're able to see here how it's different. A Lewis base can donate a pair of non-bonding electrons, and both of these have lone pairs of electrons that can be donated. And we can see here the central atom P, and we can see here between O2 we have lone pairs that can be donated. Now when I look at carbon tetrachloride, our central atom, it's not deficient, and it doesn't have any non-bonding electrons that it can donate, so CCl4 would be neither. Looking at number 6, I think you're going to think as a review, which it is. The pH of aqueous solution, we're given the concentration of hydrochloric acid. And so you're going to think this is a piece of cake after all of our ice tables. If I'm given the concentration of hydrochloric acid, I can simply take the negative log of that concentration to get the pH of 1.45. Now, for acetic acid, that is not a strong acid, it's a weak acid. So to find the pH, if I'm given the concentration of acetic acid, I do need to show my ice table. So I started with CH3COOH, going to dissociate into CH3COO and my H plus. I need to know that H plus so I can find that pH. So if I started with 0.547, I'm going to minus x plus x on both sides, giving me a Ka expression of x squared over 0.547 minus x. And we're making that assumption that that x is really small, so I can disregard that. And the Ka value for acetic acid is 1.8 times 10 to the negative 5. Once I find x is 0.00321, I can then take the negative log, and that would give me my pH of 2.49. finally, number 8. I want to find the pH of a solution that has an ammonium chloride concentration. Again, this is chloride, so it is my salt concentration of 0.060 molar, and an ammonia concentration, so that's my weak base, conjugate salt of 0.06 molar, and it gives me the Kb value. So I'm going to use my Henderson-Hasselbalch equation, but with finding pOH using the Pkb plus the log of my salt over my base. Okay, so I'm going to say my pOH is equal to 4.74, that Pkb, right? The negative log of my Kb will give me my Pkb. So 4.74 plus the log of the concentration of the salt, 0.06 divided by 0.06. That will cancel out. So then I have the pOH is equal to 4.74. To find the pH, I just need to do 14 minus 4.74, and I would get a pH of 9.26.